Hello, today we will discuss about phase velocity and group velocity. This is one of the important aspects of quantum mechanics. Mainly, the group velocity is related to wave packets. This is related to the matter wave concept. So, when a packet of waves is moving, the velocity is represented as the group velocity, and the individual wave velocity will be considered as a phase velocity. So, to start this discussion, we will use some mathematical expression. So, for simplicity, we are considering a wave which is expressed as a sine omega t minus kx, and it is moving along positive x-axis. A simple harmonic wave we have considered. Now, this part omega t minus kx is the phase part of this particular wave. So, I have written the phi of xt is omega t minus of kx. Now, phi is a function of x and t, space and time. So, we are going to differentiate the phi with respect to time. So, when you are differentiating this one, so this will be omega and this will be minus of dx dt. Now, what is dx dt? We all know that dx dt is the velocity. So, for a particular point, if the system is constant, if the phase is constant, so if phi is constant, so when you are differentiating this one, this must be equal to 0. So, one can write omega minus k dx dt, this is equal to 0. Now, we know dx dt is representing the velocity of that particular wave. So, I am representing it by u. So, u I am representing as dx dt. Okay. So, now this u normally we used to represent it by Vp, and this is known as the velocity, or this is known as the phase velocity of that particular wave. So, you can think about some monochromatic wave which is moving certain velocity. The velocity of that monochromatic wave will be considered as the phase velocity. So, either u or Vp, normally we should represent it by Vp. This is given as omega by k. So, you can just simply written as omega divided by k from this relation. So, this is the phase velocity of the system. Now, in a quantum mechanical world, the waves are superposed form. So, you really cannot distinguish between individual waves. So, normally the waves are in a form of a packet or in a form of a group. The velocity of that particular group is represented as the group velocity. So, to explain this one, we are going to consider two waves. So, for simplicity, we are going to consider two waves. So, we have considered one is psi 1, another is psi dash. So, normally there are n number of waves, they are superposing, but to have a simple mathematical expression, we are considering only two waves. Now, we can these two waves, their amplitudes are considered as same, and the phase values are almost similar. They are different, they are by some value. So, one is omega, another is considered omega dash. So, omega minus omega dash is a small value, some d omega. And same with the k and k dash, the difference between them is d of k. Now, just consider there are two waves. One can be considered as psi 1, another can be considered as psi dash. So, when they are superposed, they are basically represented by this particular wave pattern. So, mathematically what will happen? Now, see the psi which is representing psi 1 plus psi dash, this is a sine omega t minus kx plus a sine omega dash t minus k dash of x. So, it is a simple sine c plus sine d formula. So, when you have sine c by sine d, so you can represent it by sine this plus this divided by 2 and this minus this divided by 2 in case of cos. So, now what we are doing, I am just representing the first, there will be obviously two terms. So, 2 into a, amplitude is constant, 2 into a, cos into this particular term and sine into that plus term. So, cos is of minus and sine is of plus term. Now, this particular equation is representing that angular frequency omega plus omega dash and that wave number k plus k dash. So, what we are considering? We are considering same concept of that phase velocity. What we have considered, this is omega by k. We have just seen this thing. What is that individual wave case? this is omega by k. So if when you are talking about that individual wave, this is omega by k, and in that case this is omega dash by k dash. But when I have the group of the thing, so this in this case the phase will be represented, the resultant phase will be represented as omega plus omega dash and k plus k dash. We have already mentioned this thing, these values are very close to each other. So one can simply represent it by omega plus omega dash is approximately equal to 2 of omega, and k plus k dash is approximately equal to 2 of k. So obviously this is division of 2 omega by 2k. So 2 will be cancelled out, this will left out with omega by k. So the same expression what we have already calculated this thing for the phase velocity. This is the expression for the phase velocity of the individual waves. Now coming to this part, this cos, that amplitude part, that 2a into cos of this k minus k dash and omega minus omega dash. So again, when you are trying to find the velocity of this thing, it's basically the ratio between this omega minus omega dash divided by k minus k dash. So I'm representing that Vg, the group velocity of the system. Again, this is the ratio between angular frequency of the wave packet and the wave number of wave packet. What are those? This is omega minus omega dash divided by k minus k dash. So I've already mentioned this thing, these values are very close to each other. So they have elementary difference. So this difference is denoted by d omega dk, a small difference you can say. So mathematically one can say d omega tends to 0 and dk is also tends to 0. So phase velocity, this is represented in this yellow background, this is denoted as Vp, this is equal to omega by k, by the group velocity, this is denoted as Vg is equal to d omega dk. The group velocity is the velocity with which the maximum amplitude of the resultant group of waves moves. Now we need to find some relation in between phase velocity and group velocity. Now we know that Vp, this is equal to omega by k. So we are differentiating Vp with respect to k. So now when you are differentiating with respect to k, what you have got? Vp by Vk. This is obviously this omega and k both are variable with respect to k. So in first case I'm consider k as constant. So 1 by k is taken as constant. This is differentiating over omega. So d omega dk minus. Now we are differentiating, omega is taken as constant, we are differentiating over k. So it's minus 1 by k square. So take k common, 1 by k common, just simplify this one. This is 1 by k, this is equal to d omega dk. So we know what is d omega dk, this is V of g, and what is omega by k, this is also known to us, this is Vp. Now just rearranging this one, you can write that Vg, so I'm just representing the thing in terms of Vg. So Vg is simply given as Vg, this is given as Vp plus k into dVp dk. So you have this part, just rearranging this one, we got this particular expression. Now what we are doing? So we have Vp Vk, just rewriting this one, Vp Vk d lambda and d lambda dk. We are using the chain rule over there. Okay. Now what is dk d lambda? So k is given as 2 pi by lambda. So dk is minus of 2 pi divided by lambda square. Okay. So lambda dk. So d lambda dk. This is represented by minus. Sorry. This will be minus lambda square divided by 2 pi. So I'm written it wrong. This is lambda square divided by 2 pi. Divided by 2 pi. This will be 2 pi over there. This will not be there. This is lambda square divided by 2 pi. This will be just inverse of this one, dk d lambda dk. So if you have dk d lambda, so this will be minus of 2 pi divided by lambda square. And when we have lambda by d lambda dk, this will be minus of lambda square by 2 pi. So just I am replacing this one, d lambda dk, and is replacing by minus of lambda square divided by 2 pi. Now see, obviously 2 pi will be cancelled out. and the lambda, and you have the lambda square, so the minus of lambda is left. So what is the expression left? So dV of G, this is equal to Vp minus lambda dVp d lambda. Okay, so either in terms of k you can write, or in terms of lambda you can write. So this is the expression. They have a expression which is relating the phase velocity and the groove velocity. So if you know lambda of this one, so now there are two types of mediums available. One is known as dispersive medium, another is known as non-dispersive medium. So in case of dispersive medium, Vp, that is the phase velocity, is a function of lambda, whereas the non-dispersive medium, it's not a function of lambda. So in this case, Vg will be greater than Vp. When you are in dispersive medium, when waves are moving inside the dispersive medium, Vg is greater than Vp. But in case of non-dispersive medium, so Vp v lambda, it's independent of lambda, Vp v d lambda, this is equal to 0. It's independent, so it's a constant term. This is equal to 0, this variation is equal to 0, so this variation is equal to 0. So in this case, obviously, this factor is equal to 0, so Vg is equal to Vp. So this will be the case in case of non-dispersive. Now it's a graphical representation. So GIF file shows that in case of dispersive medium, if you have particle, the wave is represented by this. Okay, the spreading of wave is much lesser than the non-dispersive case. So when you have Vg is greater, so obviously this is have a broader area instead of the non-dispersive medium. Just a simple comparison. Now this particular table shows the dispersive wave for the dispersive medium. So it's not independent, it's a function of lambda, so it's not equal to 0. So Vp is not equal to Vg, obviously Vg is greater than Vp, whereas in case of non-dispersive medium, it's a constant, it's independent of lambda. So this is equal to 0. So and Vp and Vg, they are equal. Now some other relation, some in a different way I'm just representing this one. The energy of wave, the quantum wave we are talking about, we know that energy is equal to h nu. So this was given by Planck and also given by Einstein. So in case of Planck, this was the concept of quanta. The energy of quanta is given as h nu, and in case of Einstein, there is the energy of photon. This is given by h nu. So again, you can rearrange this one, h divided by 2 pi and 2 pi into frequency. So this can be written as h cross omega. So just rearranging you one, that omega is equal to E divided by h cross. So differentiate this one, d omega dE h cross. So h is constant, the Planck constant is constant obviously, and h cross is also constant, h by 2 pi, this is also constant. This is one of the equation, d omega dE dk. Now from the de Broglie's hypothesis, we know P is equal to h divided by lambda. So h divided by 2 pi divided by lambda. This is h cross k. So again, if you are differentiating this one, so d dk, this is equal to dp divided by h cross. Now you have d omega, you have dk. So you can just get the phase velocity, d omega dk. You can get the group velocity, d omega dk. And what about the phase velocity? The phase velocity is obviously omega by k. So when you have omega by k, multiply denominator and numerator with h cross. So this becomes h cross omega, and this becomes h cross k. So what is h cross omega? We have just already calculated. This is the energy of the wave, energy of the quantum wave. This is E. And what is h cross k? I've just checked this one. This is the de Broglie's momentum. This is P. So this is E by P. And what of the phase velocity? Now you know we have d omega dk. So obviously d omega dk, we have already calculated this thing. Group velocity is equal to d omega dk. So what is d omega? D omega is E by h cross, E by h cross. And what is dk? dk is equal to dp h cross. Now this can be written as 1 divided by dp h cross. So you are just rearranging this one. H cross will be cancelled out. What is finally left? This is dE dP. dE dP. Now, if you are talking about light, so the phase velocity can be considered as Vp is equal to E by K. So the energy in this case, this is written as mc square, the Einstein's relation, mc square. And what is P? P is the momentum of the system. So mass into velocity. Whose velocity? The particle velocity. So mass of the same particle, so they will be cancelled out. This left out with c square divided by Vg. So we have the relation Vp Vg, this is equal to c square. Now the two cases we will discuss. Now here we have the relativistic case and we have the non-relativistic case. So what is relativistic case? When particle moves with velocity at least 50% of the velocity of light. That means we can just consider c divided by 2. The velocity of the particle is greater than equal to c by 2. So the 50% of the velocity of light. Then the system will be considered as the relativistic system. So in this case, the Dirac equation will be applicable. So what is Dirac equation? Dirac equation is given by E square. This is equal to P squared C square plus m0 square c to the power 4. This is mc square whole square. So what is m0? M0 is the rest mass of the particle. Now just differentiate this one. So E square you have, this will be 2E dE, and when you are differentiating this one, these are common. This part can be written as c square. C square is a constant term, it's taken it out, and we are differentiating this one, this is 2p dp. Now we all know that the velocity or speed of light is a constant, so c square will be taken as constant. So in this case, this is c to the power 4 is also constant, and obviously the rest mass of the particle is constant. So this factor is equal to 0. So this is 2e dE, this is equal to c square 2p dp. Again, you have dE dP. So just I am rewriting this one, dE dP. So what is dE dP? We have just calculated this one. dE dP, this is given the group velocity. So you just try to find the group velocity of the system. dE dP, what is dE dP? So just rearranging this one, this is gives you c square P divided by E. Again I am writing that c square into m into v, that momentum part, m into the particle velocity, and mc square. So c square and m will be cancelled out. This is equal to v. Okay. So again this is equal to the group velocity. So we can just think about, this is a particle, we are talking about the particle velocity, which is equal to group velocity. V Vp is the group velocity. So the group velocity is equal to the particle velocity. Now take the case of non-relativistic. So in case of non-relativistic, we are considering velocity is much lesser than velocity of light. Even it's much lesser than 50% of velocity of light. It's a normal velocity we are talking about. So in this case, that energy is given as p square by 2m. So this is basically half mv square, the normal kinetic energy. And the momentum is the m into v. Again, just get the differentiation. dE dP, just I am differentiating this thing, dE dP. So what you will get, this will be 2p dP. Okay, so 2 will be cancelled out. Okay, so this will be p square d. So when you are differentiating p square, so when you have p square, so you are differentiating p square, so this will be 2p dP. So what we are doing, so you have dE over there, you are differentiating dE over there, and you have dP over there. I am taking dP over there. So dE dP, we are using the chain rule. So what is left? This is left with 2 of p, and here you have 2 of m. So this will simply left out with p by m. Now what is p? P is the momentum. Momentum is given as m into v. So what is v? V is the velocity of the particle. So mm will cancel out. This left out with the velocity. Velocity of the particle. Now you know dE dP, this is the group velocity. So obviously the particle velocity is equal to group velocity. This is the thing what we try to prove over there. In both cases, the group velocity of de Broglie's wave is same as the particle velocity. So when you think about quantum mechanics, we need to think about a group is moving, a wave packet is moving. That wave packet is representing the particle which is moving in this direction. So this wave packet is represented by some mathematical expression, something like this. So for simplicity, we have considered only two waves, but there may be infinite number of waves. They will superpose and will form the packet over there. Now the wave packet, the velocity of the wave packet will be represented by Vg, the group velocity. Now this wave packet is basically the extension or the simplest form of that wave function. The wave function is the extended form of the concept of wave packet. So it is very simplified form we are representing mathematically by this. So wave function, which is represented by psi, is a function of space and time. It's only a mathematical function. There is no physical significance of this. It's only function of space and time, which is representing the quantum particle aspects. But the probability of the finding particle, this is the most important thing in case of quantum mechanics. The probability of finding the particle, anyway you can think about probability of finding the particle, where the particle will be available. This is represented by the P, the probability part, and this will be integration over this function. So it's a complex function, e to the power I kx minus omega t. When you have e to the power I kx minus omega t, obviously the psi star, the complex conjugate, is given as e to the power minus I kx minus omega t. Okay. So in a very ideal case, so e to the power I and e to the power minus I, when you are multiplying this thing, so obviously this will give you 1. The probability will be considered as normalized. And the most important aspects of the wave function is, so mathematically this should be single value. So single value of space and time, there will be single value of psi. This must be continuous, no break should be there within this particular function, and this must be finite in nature. So for any value, this should not give a infinite result. So today we will discuss about the concept of wave packet, the concept of group velocity, phase velocity, and the extended part, the concept of wave function in case of quantum mechanics.